Okay, now we're gonna do chapter 11. This gets grouped in with chapter 8 because the only thing we're gonna do in chapter 11 is how to make confidence intervals for the standard deviation. We talked about making confidence intervals for the mean and a proportion, and those are usually two parameters that we need when talking about any distribution. But another parameter we typically need when talking about distributions is the standard deviation. Okay? So, say we don't know the population standard deviation and we want to find a range of the population standard deviation, we could construct a confidence interval for them. Okay? Now, to do this, we need to talk about a new distribution. So far, we had the z distribution, which you use the z distribution for the mean if you know the population standard deviation and for a proportion. We had the t distribution, which was used to make a confidence interval for the mean if you did not know the population standard deviation. Now, this is going to be the chi-squared distribution. Okay, chi, C-H-I. This is Greek letter chi. It looks like an X. It's like a fancy X. It's got like a curly part on that part and a straight part like that. And then chi-squared. Like that. This is just notation. It has nothing to do with squaring the number right here, okay? This is just notation. When we find these values, you are not going to square them, okay? Again, just notation. The squared's there, it's how the distribution is named, okay? Now, let's talk about the characteristics of a chi-squared distribution. It is very different than our t distribution and our z distribution. All chi-squared values are greater than or equal to 0. Okay, so the reason being, all the graphs look something like this. Starts at 0, goes like that. And you could see the graph. I have another picture on the lower on the page. That's because chi-squared is equal to, here's the formula for chi-squared, it's n minus 1, so the sample size minus 1, times the standard deviation squared, the sample standard deviation squared, divided by the population standard deviation squared. So if this is a squared value, this is a squared value, that's positive, n minus 1. N is always positive, it's your sample size. So everything here is a positive number. Okay? So that would explain why our values for our chi-squared graph are always greater than or equal to 0. They're always positive. Now, each graph has a degree of freedom. Okay? This is just like the graph on bullet point 3. We could also talk about bullet point 3. It says the curve is asymmetrical and skewed to the right. So you see, pull a little to the right, pull a little to the right. They're asymmetrical. If I were to draw a line right down the middle of here, it would not flip over and match the right side. Okay, now, for every degree of freedom, there's a different graph. Just like the t distribution. For every degree of freedom, there was a different graph. Okay? So now the notation for this, the degrees of freedom. Formula for the degrees of freedom here. N minus 1. It's the same thing as the t distribution. N minus 1. Alright, so some notation. You're always going to know your sample size, so you can always compute your degrees of freedom. So your distribution is going to be chi-squared with however many degrees of freedom, okay? Again, you always know your sample size, subtract 1, that's the number that would go down here. So just for an example, we could say our distribution is chi-squared with degrees of freedom of 9. This would imply our sample size would be 10, because n minus 1 is 9. Okay. Now, to compute these graphs, the mean is always the degrees of freedom, and then the standard deviation is always the square root 2 times the degrees of freedom. So that's if you wanted to find the mean of this graph and the standard deviation of the graph. And then we could, if we're using the central limit theorem, we could use this as the mean. We would divide this by the square root of n. We could use a normal CDF, stuff like that. Okay. So what we're going to find are called the chi-squared right critical value and the chi-squared left critical value. Oh, I forgot the word left. Left critical value. So we want an estimate for the standard deviation. Let's go ahead. Chi-squared is equal to n minus 1 times s squared divided by sigma squared. If you were just to interchange these values right here, you get sigma squared is equal to n minus 1 times s squared divided by chi squared. Okay? What we really want is the interval. Okay? So there's going to be a chi-squared left value and a chi-squared right value. And then this is for the variance. It's going to be n minus 1 times s squared divided by the chi-squared right value. And then n minus 1 s squared divided by the chi-squared left value. We need to find these values, okay? Just like we would find the values, these are our critical numbers. Just like our z of alpha divided by 2, or our t divided by, or t sub alpha divided by 2, same idea here. Now, you need to find them individually. Previously, the graph was symmetric, so when you found the negative version, we were just able to make it positive right away. These are going to be two different numbers, so like I said, you have to find them individually. So, now, here's how we're going to construct our confidence interval. You're told the sample size, you're told the sample standard deviation, or you could figure that out if they gave you a list of data. You could plug it in the calculator and use one variable stats. So look at the numerator over here. It's the same exact thing. So we know the numerators. We don't know what these are. We have to find them. Okay. Now notice the chi-squared right critical values on the left denominator. The chi-squared left value is on the right denominator. That's because this value is going to be larger than this value. The numerators are the same. So when you divide by a larger number, the overall number is going to be smaller. When you divide by a smaller number, the overall number is going to be larger. So we get the small number on the left, large number on the right. So let's go ahead and talk about how to find these critical values. Now, if you have my notes, scroll down to the second page, you're gonna see a table, and this is the chi-squared distribution table. If you notice on the right-hand side, or sorry, the left-hand column over here, you have degrees of freedom. 1, 2, 3, 4, 5, 6, and it goes on and on. Just like in the T distribution, you have the degrees of freedom on the left. So you need to look at find your row, whatever degrees of freedom you have, find the row, and then your critical values are going to come from looking at the row and picking out the right columns. Now, in the columns up here, so it looks something like something like that and so on. And you see 0.9, 0.975, 0.99, 0.975, 0.95, 0.9, one more, and then it goes 0.1. Let's do one more. 0.05. If you notice and look at this table is symmetrical about this black line right there. It happens to be the exact middle of the table. And what I mean by it's symmetrical, 0.1 plus 0.9 is 1. 0.05 plus 0.95 is 1. This next one is 0.025. 0.025 plus 0.975 is 1. 0.99, so this is 0.01. They all add up to 1. It's symmetrical. So, how you're going to do this is you look at your confidence level. Whatever your confidence level is, 99, 95, 90. We haven't seen 97.5 that much. But the left side of this black bar is going to correspond to whatever your confidence level is on this side. On the other side of this black bar in the middle, these are going to be your alpha values. Okay? Not alpha over 2. Just your alpha value, okay? So to find alpha, remember just 1 minus the confidence level. So let's take a confidence level of 0.9. That means alpha would be 0.1. Right here. You would just look in this column for whatever degrees of freedom that you want. So let's say you wanted 6 degrees of freedom. This would be your chi-squared left value. This would be your chi-squared right value. It's the left value because it's coming from the left side of the table. This is the right value because it's coming from the right side of the table. Okay? Now, if you were to notice, 0.1, 0.9, they match up. If I had instead of a confidence level of 0.9, let's say I have a confidence level of 0.99. It's the last column. Sorry, first column. So then when I find alpha, that's going to be 0.01. That's the last column. They correspond to one another. So if you just find one, let's see, this is 1, 2, 3 away from the middle. So 1, 2, 3 away from the middle. This would be your left one. This would be your right one. Okay? So that's how you read this table. Unfortunately, there is not a calculator function that allows us to just type in the degrees of freedom and the confidence level, and it outputs the critical values. There's no inverse chi-squared like we have an inverse t and an inverse norm. Okay, so these values will have to be pulled from the table. On the test, I will provide you with any tables you may need, okay?